Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. 1 billion years ago, 1,000 million years in Earth's past, our planet would have been utterly alien to modern human eyes. From the vantage point of space, this ancient version of our home presented a dramatically different visage than the familiar blue marble we know today. Orbital sensors and spacecraft would have captured a world both familiar in its general shape, but startlingly foreign in its details, a testament to our planet's remarkable evolutionary journey. The Earth of 1 billion years ago existed in what geologists call the late Proterozoic eon, specifically during a period known as the Tonian. This critical chapter in Earth's development falls within the broader Precambrian, a vast stretch of time encompassing roughly 88% of our planet's entire history. To comprehend the scale of this temporal distance, if Earth's entire 4.5 billion-year history were compressed into a single 24-hour day, we would be discussing a world that existed around 5.3 hours before midnight, while human civilization would emerge only in the final 17 seconds. From space, the most immediately striking difference would be the continents. Rather than our familiar 7 continents spread across separate landmasses, Earth during the Tonian period featured a supercontinent called Rodinia. This massive landmass, whose name derives from the Russian word for motherland, had assembled between 1.3 and 900 million years ago through the collision of earlier continental fragments. Unlike our modern configuration, Rodinia concentrated nearly all planetary landmass into a single massive continent centered around what is now the South Pole, surrounded by a vast global ocean. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The coloration of this ancient Earth would also appear dramatically different. Modern Earth owes its distinctive blue appearance primarily to our oceans, which cover 71% of the surface. The characteristic white cloud patterns and green-brown landmasses complete the palette we recognize. However, 1 billion years ago, this color scheme would be fundamentally altered. Most significantly, the landmasses would appear barren reddish-brown, devoid of the green vegetation that characterizes modern continents, as land plants wouldn't evolve for another 500 million years. The oceans themselves might have possessed a slightly greenish tint, rather than the vibrant blue we know today. This subtle difference stems from their chemical composition, which featured higher iron content and dramatically different dissolved mineral profiles. Additionally, with no land plants to regulate atmospheric composition, carbon dioxide levels were significantly higher, perhaps 20 to 100 times present levels, creating a dramatically enhanced greenhouse effect. Looking at the atmosphere from space, another major difference would be immediately apparent. Oxygen levels were substantially lower, perhaps just 1 to 10% of present atmospheric oxygen. The sky itself would have appeared hazier and possibly tinged with orange-brown tones from various suspended particles and chemical compounds. Cloud patterns would have been different as well, driven by altered atmospheric circulation patterns resulting from Rodinia's unique continental configuration and the stronger greenhouse effect. Perhaps most striking would be the absence of polar ice caps. In our modern era, bright white ice caps at both poles are distinctive features visible from orbit. 1 billion years ago, however, Earth was in a prolonged greenhouse phase with significantly warmer global temperatures, too warm for permanent polar ice to form. Only occasionally during this period did brief intense glaciations occur, temporarily painting portions of Rodinia white with ice before receding again. Dominating the late Proterozoic Earth, Rodinia represented a fundamentally different planetary arrangement than our familiar modern continents. This massive supercontinent stretched across roughly 130 million square kilometers, nearly equivalent to all modern continental landmass combined. From orbit, this enormous single landmass would have created a visual imbalance across the planet's surface, with one hemisphere dominated by Rodinia, while the opposite side displayed an uninterrupted expanse of global ocean nicknamed Morovia by paleocontinental researchers, from the Russian word for global. The position of Rodinia remains the subject of ongoing scientific debate, though most reconstructions place its center near the equator or southern hemisphere. Its precise shape also remains contested, though the prevailing sweat hypothesis, southwest US and East Antarctica, suggests western North America connected directly to eastern Antarctica, with Australia nestled between India and western North America. Other fragments of modern continents, including pieces of South America, Africa, and Eurasia, completed this ancient landmass through connections that would be entirely unrecognizable today. What made Rodinia particularly distinctive was its extensive coastline. Unlike previous supercontinents that formed more circular, compact arrangements, Rodinia featured numerous peninsulas and partially enclosed seas. This created a sprawling, irregular shoreline that would have been visible as jagged edges from space, particularly along what scientists call the Proto-Pacific Ocean Basin. These coastal zones would have experienced intense tidal forces as the Moon orbited closer to Earth than it does today, perhaps just 270,000 kilometers away compared to the current 384,000 kilometers. This proximity created tides potentially 2 to 3 times stronger than modern oceans experience. The continental shelves surrounding Rodinia extended far into the surrounding Moravia Ocean with broad, shallow platforms. These extensive continental shelf systems would have appeared from space as lighter-colored halos surrounding the main landmass, particularly visible where sediment-rich water created distinctive plumes extending into deeper waters. Without land plants to stabilize soil, erosion rates would have been dramatically higher than today, causing substantial sediment flow into these coastal regions after precipitation events. The interior of Rodinia would have featured numerous impact craters still visible from orbit, relics from the late heavy bombardment period when asteroid impacts were more common. Though many of these ancient impact structures would have eroded significantly by 1 billion years ago, several larger impact basins would remain as distinctive circular features. Additionally, extensive fault systems and mountain ranges created by the tectonic collisions that formed Rodinia would have been visible as linear features crisscrossing the continent's surface. Most strikingly different from modern Earth would be the absence of internal seas like our Mediterranean or Caribbean. With nearly all continental mass consolidated into Rodinia, the planet featured primarily 2 environments, continent and open ocean. This arrangement created more extreme climate conditions across Rodinia, with coastal regions experiencing moderate temperatures while continental interiors suffered dramatic temperature swings between day and night. Due to the absence of water's moderating influence, the Moravia Ocean itself covered approximately 70% of Earth's surface, similar to modern ocean coverage, but distributed very differently. From orbit, this vast, uninterrupted expanse of water would have appeared as an enormous blue-green plain stretching across an entire hemisphere. Without significant land masses to interrupt oceanic currents, circulation patterns would have been simpler, but more powerful than today, creating massive gyres visible from space through temperature differentials and biological activity. The oceanic crust beneath Moravia was younger on average than modern oceanic crust, due to higher rates of seafloor spreading and subduction. This increased volcanic activity along mid-ocean ridges would have been visible from space as faint linear features where upwelling magma created new seafloor. These ridges generated chains of volcanic islands that would have appeared as tiny specks dotting the otherwise uninterrupted oceanic expanse, the only land visible across vast stretches of the planet opposite Rodinia. The atmosphere enveloping Earth 1 billion years ago would have created a dramatically different appearance from orbit compared to our contemporary planet. Most immediately noticeable would be its coloration, rather than the crisp blue atmosphere we associate with Earth today. The Tonian atmosphere likely presented as a hazier, possibly yellowish-brown tinted envelope surrounding the planet. This distinctive appearance resulted from its radically different chemical composition compared to our modern atmosphere. Oxygen levels during this period reached only about 10 to 15% of total atmospheric volume, considerably lower than our current 21%. This reduced oxygen level created profound differences in atmospheric chemistry and optical properties. Meanwhile, carbon dioxide concentrations were substantially elevated compared to pre-industrial levels, perhaps reaching 5,000 to 10,000 parts per million, 10 to 25 times higher than modern levels. This CO2-rich atmosphere served as a powerful thermal blanket, trapping solar radiation and creating greenhouse warming that prevented ice formation despite the sun being approximately 6% dimmer than today due to its progressive brightening. Over its lifetime, methane, a greenhouse gas 28 times more potent than CO2, likely existed at levels hundreds of times higher than today. This methane primarily originated from methanogenic microbes thriving in oxygen-poor environments throughout the oceans and terrestrial muds. From orbit, this complex atmospheric cocktail created a different optical appearance, scattering light differently and potentially creating more dramatic sunrise and sunset effects along the planetary terminator, the dividing line between day and night sides. Water vapor distribution would have differed dramatically as well. With significantly warmer global temperatures, evaporation rates from the Moravia Ocean would have been substantially higher. This created a more moisture-laden atmosphere, supporting thicker, more extensive cloud systems visible from space. These cloud patterns would have organized differently than modern systems due to the unique geography of Rodinia and the altered global circulation patterns it generated. The atmospheric circulation itself operated under fundamentally different parameters. Modern Earth's atmospheric flow is significantly influenced by the distribution of continents and oceans, creating complex patterns of air movement. In contrast, the Rodinia-dominated planet featured more symmetrical circulation patterns due to the simplified geography of one supercontinent opposed by a global ocean. This created more predictable but potentially more extreme weather systems that would have been visible from orbit as massive, organized cloud bands and vortices. Temperature. Gradients on Earth 1 billion years ago followed different patterns than modern distribution. Today's Earth features distinct latitudinal temperature bands, with equatorial regions receiving the most solar energy, while polar regions receive the least, creating our familiar climate zones. The Tonian Earth, however, experienced less extreme pole-to-equator temperature differentials due to more efficient heat transport in the greenhouse-enhanced atmosphere. From orbit, this would have appeared as more uniform thermal patterns in infrared observations, with less dramatic temperature variations between equatorial and polar regions. Seasonal effects would have manifested differently as well. The configuration of Rodinia created continental areas experiencing extreme seasonality, much more pronounced than most modern land areas. Interior regions of the supercontinent, located far from the moderating influence of oceans, experienced dramatic temperature swings between seasons. Meanwhile, the vast Moravia Ocean maintained more stable temperatures year-round. This created visible seasonal changes in cloud patterns and atmospheric circulation observable from space as enormous weather systems migrated across the planet annually. Perhaps most striking would be the absence of polar ice caps and glaciated regions that characterize our modern planet. Without these highly reflective white surfaces at high latitudes, Earth's overall albedo, its reflectivity to incoming solar radiation, would have been lower. This created a positive feedback loop, reinforcing the greenhouse conditions as less solar energy was reflected back to space. From orbit, the planet would have appeared slightly darker overall than modern Earth, absorbing more incoming solar radiation. The appearance of storms from space would have been considerably different. As well, higher overall temperatures and greater water vapor content created the conditions for more energetic storm systems. Massive cyclonic structures likely developed over the warm Moravia Ocean, potentially growing larger than modern hurricanes or typhoons due to the uninterrupted oceanic fetch, allowing storms to organize without landmasses disrupting their formation. These enormous weather systems would have been visible from orbit as vast spiral structures crawling across the planet's surface. The biosphere of Earth 1 billion years ago existed in a state fundamentally different from our modern world. From orbit, the most immediately striking feature would be the absence of obvious surface vegetation. The familiar patchwork of greens, yellows and browns that characterize continental surfaces today, the visible signature of forests, grasslands and shrublands, was entirely absent. Land plants wouldn't evolve for another 500 million years, leaving continental interiors largely barren from a biological perspective. However, this doesn't mean Earth lacked a biosphere. Life had already existed for over 3 billion years by this point, evolving sophisticated microbial ecosystems that would have been visible from space through their collective impact on planetary appearances. The dominant life forms were entirely microbial, bacteria, archaea, and the relatively recently evolved eukaryotes, organisms with cell nuclei. These microscopic organisms collectively transformed Earth's appearance through their metabolic activities and massive population sizes. Most visibly, shallow coastal waters likely displayed vivid colors from microbial mats, layered communities of microorganisms that formed carpet-like structures in intertidal zones and shallow waters. These mats featured distinct layers of different photosynthetic microbes organized according to light penetration and oxygen tolerance. From orbit, these would have been visible as distinctive color bands following coastlines, greens, purples, reds, and oranges, depending on the dominant pigments in the microbial communities. Particularly notable would have been stromatolites, layered, sedimentary structures formed by microbial mats that trapped and bound sediments over time. These structures could grow quite large, forming reef-like formations in shallow waters. During the Tonian period, stromatolites reached their peak diversity and abundance after dominating shallow marine environments for over 2 billion years. From space, extensive stromatolite reefs would have appeared as lighter-colored patches in coastal waters, particularly visible in regions where Rodinia featured shallow continental shelves. Open ocean areas would have showcased different biological signatures visible from orbit. While individual microbes are far too small to see from space, their collective impact on water coloration would have been substantial. Various types of photosynthetic bacteria and early algae created distinctive blooms in nutrient-rich waters, potentially visible as large greenish or reddish patches spanning hundreds of kilometers across the Moravia ocean surface. These oceanic blooms would have appeared particularly prominent around upwelling zones, where nutrient-rich deep waters reach the surface. Without today's complex food webs, including fish and other larger organisms to consume these blooms, they could grow more extensive than modern algal blooms. The resulting patches of discolored water would have created dynamic patterns visible from orbit as they formed, dispersed, and reformed according to changing ocean conditions. Continental interiors, while lacking macroscopic vegetation, weren't entirely lifeless. Microbial communities likely colonized land surfaces in thin but widespread biofilms. Particularly in areas with consistent moisture, these communities would have been dominated by cyanobacteria and other photosynthetic microbes capable of surviving. The harsh ultraviolet radiation that reached the surface due to the absence of an ozone layer. From orbit, these biological crusts might have appeared as subtle darkening of land surfaces, particularly visible after rainfall events when dormant microbes rapidly activated. The biological influence extended beyond direct visual signatures to include atmospheric effects. Photosynthetic microbes in the oceans produced much of Earth's oxygen, creating the conditions that would eventually support complex life. While oxygen levels remained lower than today, biological activity created distinctive atmospheric chemistry that influenced how the planet appeared from space by altering atmospheric composition and optical properties. Seasonal variations in microbial activity would have created visible changes from orbit as well. During warmer periods, microbial populations in both oceans and on land surfaces would expand rapidly, potentially changing regional coloration. These biological responses to seasonal changes would have added another dynamic element to Earth's appearance from space, with visible shifts in coastal and oceanic coloration following seasonal temperature patterns. Most significantly, this microbial-dominated world was undergoing a pivotal transition during the late Tonian period. Fossil evidence suggests that around 1 billion years ago, more complex eukaryotic organisms were diversifying, including the earliest multicellular algae. These evolutionary developments, though not immediately obvious from orbital observation, were setting the stage for the later explosion of complex life that would dramatically transform Earth's appearance in subsequent eons. The weather systems of Earth 1 billion years ago operated under fundamentally different parameters than our modern world, creating visual spectacles that would have been immediately apparent from orbit. Perhaps most striking were the enormous storm systems that developed over the vast, uninterrupted Mirovia Ocean. Without continental landmasses to disrupt cyclonic formation, storms could organize into massive structures spanning thousands of kilometers, substantially larger than the largest modern hurricanes. These superstorms would have been visible from space as vast spiral structures with distinctive eye formations, crawling slowly across the planetary surface. Their cloud formations would have appeared different from modern hurricanes, however, featuring different vertical development patterns due to the altered atmospheric composition. Higher carbon dioxide and water vapor content created more energetic storm systems with potentially higher cloud tops, making them appear as towering white structures against the blue-green ocean background. Precipitation patterns across the planet followed dramatically different distribution than today's Earth. Modern precipitation is heavily influenced by the arrangement of continents and oceans, mountain ranges, and prevailing wind patterns. The Rodinia-dominated Earth featured simpler but more extreme precipitation gradients. Coastal regions of the supercontinent received enormous amounts of rainfall as moisture-laden air from Mirovia moved onshore, potentially creating persistent cloud bands visible from orbit along continental margins. Meanwhile, the vast continental interior experienced extreme aridity as moisture-bearing weather systems weakened progressively toward the center of Rodinia. This created a striking visual contrast from orbit, the coastlines appearing frequently cloud-covered, while interior regions remained perpetually clear and dry. During seasonal shifts, monsoonal patterns likely developed on scales far exceeding modern monsoons, with enormous wet and dry cycles affecting vast regions simultaneously. Lightning activity would have created another spectacular visual element, observable from space during nighttime passes. The different atmospheric composition, particularly the higher water vapor content, coupled with greater convective energy in storm systems, potentially generated more frequent and powerful lightning discharges. From orbit, night-side observations would have revealed massive lightning storms illuminating cloud systems over both the ocean and coastal regions, appearing as bright flashes against the dark planetary surface. The absence of mountain ranges, comparable to modern Himalayas, Andes, or Rockies, all formed much later through tectonic processes still ongoing today, meant that orographic precipitation patterns differed significantly. Rather than concentrated rainfall along mountain fronts, characteristic of our modern world, precipitation likely followed broader patterns determined by global circulation and continental position. This created less sharply defined rainfall boundaries. Visible from space, dust storms represented another dramatic weather phenomenon visible from orbit. Without vegetation to stabilize soil surfaces, Rodinia's arid interior regions were susceptible to massive dust events when seasonal winds reached sufficient strength. These events could have lofted enormous quantities of fine particulates into the atmosphere, creating dust clouds visible from space as brownish-yellow plumes extending from continental interiors. These dust events might have persisted for weeks, or even months, gradually spreading fine particles across thousands of kilometers. Seasonal patterns created another layer of visual complexity observable from orbit. The extreme seasonality experienced particularly in mid-latitude regions of Rodinia created dramatic annual shifts in cloud cover, precipitation, and surface appearance. During summer months in a given hemisphere, intense heating of the continental interior created strong thermal low-pressure systems drawing moisture inward from coastal regions. This generated distinctive cloud patterns visible from space as moisture-laden air moved inland before dissipating over the arid interior. Winter seasons presented different patterns, with clearer skies over much of the continent and potentially increased storminess over warmer ocean waters. These seasonal shifts would have been apparent from orbit as annual migrations of predominant cloud patterns and storm tracks across the planetary surface. Without the complex topography and land-sea distributions of our modern world, these patterns would have presented more symmetrical, predictable annual cycles. The diurnal cycle, the daily pattern of heating and cooling, created its own visible effects from orbit. During daylight hours, intense solar heating of Rodinea's land surface generated strong convective systems visible as afternoon cloud development over otherwise clear continental regions. These daily convective patterns would have been particularly prominent along coastal zones where moisture availability supported cloud formation. From space, this would appear as a predictable daily cycle of cloud development and dissipation, following the terminator line between day and night as it swept across the planet. Most significantly, extreme weather events likely occurred with greater frequency and intensity than comparable modern systems. The combination of higher global temperatures, elevated greenhouse gas concentrations, and simplified continental configuration created conditions favorable for weather extremes. That would have been readily apparent during orbital observation of the planet. Earth 1 billion years ago was a dynamically active planet, its surface continuously reshaped by powerful geological forces that would have been visible from orbit. The most fundamental of these processes, plate tectonics, operated with greater vigor than today. Geochemical evidence suggests internal heat flow from Earth's core and mantle was approximately 25 to 30% higher than present levels, driving more energetic crustal movement and associated volcanic activity. This enhanced tectonic activity manifested visibly along the boundaries where crustal plates interacted. Subduction zones, regions where oceanic crust plunged beneath continental material, created distinctive linear features along Rodinea's margins. These tectonic boundaries would have been recognizable from space through chains of volcanoes forming island arcs and coastal mountain ranges still actively developing through crustal compression. Without vegetation coverage, these geological structures would have been clearly visible as bare rock formations with distinctive morphology reflecting their origin. Volcanic activity itself created spectacular features observable from orbit. The higher internal heat flow supported more numerous and energetic eruptions than our modern planet experiences. Large-scale eruptions would have been visible as bright thermal anomalies during active phases, with enormous ash plumes extending into the upper atmosphere and potentially circling the globe. These eruption plumes would have appeared as distinctive grayish-brown clouds, expanding outward from source volcanoes, gradually dispersing into thinner haze affecting global atmospheric transparency. Particularly notable would have been submarine volcanism along the globe-spanning oceanic ridge system, where new crust formed as tectonic plates separated. This underwater volcanic activity created massive hydrothermal vent fields where superheated mineral-rich water erupted into the ocean. While the underwater vents themselves wouldn't be directly visible from orbit, their effects sometimes were, creating distinctive water discoloration through mineral precipitation and supporting blooms of chemosynthetic microbes that appeared as colored patches on the ocean surface. Impact events, collisions between Earth and asteroids or comets, occurred more frequently 1 billion years ago than today. While the most intense bombardment periods had ended billions of years earlier, impact rates remained higher than modern levels. Fresh impact structures would have been readily apparent from orbit as distinctive circular features with central peaks and surrounding ejecta patterns radiating outward. Without vegetation or weathering to obscure them, even relatively small impact craters would have remained visible for millions of years as distinctive scars on the landscape. The supercontinent cycle, the process through which continents assemble and disperse over hundreds of millions of years, was in a crucial phase during this period. Rodinia had fully assembled by around 1.1 billion years ago and would begin breaking apart shortly after the 1 billion year mark. This imminent fragmentation was likely already manifesting through developing rift systems, linear features where the continent was beginning to split apart. From orbit, these nascent rifts would have appeared as dark lines cutting across continental surfaces, often associated with increased volcanic activity and fault systems. Mountain-building processes created significant elevated terrain visible. From space, particularly along collisional boundaries where continental fragments had joined to form Rodinia. These mountain ranges, while significant, would have appeared different from modern mountains. Without vegetation covering them, their bare rock surfaces would have been directly visible, revealing structural features like folded rock layers and fault lines that would be obscured in our modern vegetated world. Erosional processes operated under different parameters as well. Without plant roots to stabilize soil and sediment, erosion rates were substantially higher when precipitation occurred. This created more extensive alluvial fan systems and sediment plumes visible from orbit, particularly after major rainfall events. River systems carved more dynamic, braided patterns across the landscape, rather than the more stable meandering rivers common in our vegetated world. These river systems would have been visible from space as networks of channels continually shifting, their courses across broad floodplains. Large-scale sedimentary features represented another category of visible geological structures. Vast desert regions in continental interiors featured extensive dune systems organized into patterns visible from orbit. Without vegetation to interrupt their formation, these dune fields could achieve enormous scale, creating wave-like patterns stretching across hundreds of kilometers. Similarly, mudflats and evaporate deposits in seasonal lakes would have formed distinctive light-colored patches in continental basins where water occasionally accumulated before evaporating. The ongoing reshaping of Earth's surface through these geological processes created a dynamic planetary appearance that would have shown noticeable changes, even over relatively short observational periods of decades or centuries, a planet visibly evolving through powerful internal and external forces. Earth at the 1 billion-year mark stood poised at a critical evolutionary threshold, a planet caught between its ancient microbial-dominated past and the complex multicellular future that would eventually transform its appearance and systems. This transitional status would have been subtly evident from orbital observation through various emerging patterns and processes that foreshadowed Earth's future trajectory. The Rodinia supercontinent configuration itself represented a temporary arrangement in Earth's ongoing tectonic evolution. Geological evidence indicates that around 950 million years after our observational period, Rodinia began breaking apart through massive rifting events. The initial stages of this continental fragmentation were likely already developing 1 billion years ago, visible from orbit as subtle fault systems and areas of thinning crust where magmatic activity was increasing. These nascent rift zones represented the first hints of the dramatic continental reconfiguration that would eventually produce our familiar modern continents. Biologically, Earth was experiencing equally momentous transitions. The fossil record indicates that around this time, more complex eukaryotic organisms were diversifying significantly. While individual microorganisms remained invisible from space, their collective ecological impact was increasing. New types of algae and early protists were evolving more complex cellular structures and behaviors, setting the stage for the later evolution of multicellular organisms that would dramatically transform planetary surfaces and oceans. The first, experiments with multicellularity, were likely already underway in marine environments. Fossils from slightly after this period show evidence of primitive multicellular algae developing in shallow waters. While these early multicellular innovations weren't yet sufficiently widespread to create visible impacts from orbit, they represented the vanguard of a biological revolution that would eventually transform Earth's appearance through the development of larger, more complex organisms. Atmospheric composition continued its own gradual transformation. The gradually increasing oxygen levels, though still much lower than today, were approaching thresholds that would eventually support more metabolically demanding multicellular life forms. From orbit, this ongoing atmospheric evolution manifested through subtle changes in atmospheric coloration and optical properties, with a gradually clearing haze as certain atmospheric components were oxidized and removed. Climate patterns showed signs of impending change as well. Though Earth remained in a predominantly warm greenhouse state, geological evidence indicates that major glaciation episodes would begin affecting the planet within the next 100 million years after our observation period. These coming snowball Earth episodes when ice coverage expanded dramatically across the planet, would represent some of the most extreme climate fluctuations in Earth's history. The earliest indicators of this climatic instability might have been detectable from orbit through changing atmospheric circulation patterns and ocean temperature distributions. Ocean chemistry was undergoing its own transformation. Changing ratios of dissolved minerals, gradually increasing oxygen content in surface waters, and evolving microbial communities were collectively altering how the oceans appeared from orbit. These chemical shifts, while subtle, represented critical preconditions for the later explosion of complex marine life that would characterize the Cambrian period 500 million years later. The planetary scale cycling of elements, carbon, oxygen, nitrogen, phosphorus, and others, was operating under parameters substantially different from both earlier periods and later eras. These biogeochemical cycles connected the lithosphere, hydrosphere, atmosphere, and embryonic biosphere in complex feedback systems that regulated planetary conditions. From orbit, the impacts of these cycles would have been visible through atmospheric composition, ocean coloration, and the distribution of various surface features related to mineral deposits and biological activity. Solar output during this period was approximately 6% lower than modern levels, as part of the Sun's gradual brightening throughout its lifetime. This reduced solar radiation was substantially offset by enhanced greenhouse effects from higher carbon dioxide and methane concentrations. However, this different energy balance created distinctive circulation patterns in both atmosphere and oceans that would have been apparent from space through cloud distributions and sea surface temperature patterns. Perhaps most profoundly, Earth at 1 billion years ago represented a unique moment in planetary evolution, a world that had already been transformed by life through the development of an oxygen-containing atmosphere, but had not yet experienced the explosion of complex multicellular organisms that would later reshape its surface features and systems completely. From orbit, this transitional Earth presented a portrait of a planet in the midst of becoming, its appearance hinting at both its ancient history and its remarkable future. As we observe this ancient version of our homeworld, we gain profound perspective on Earth's evolutionary journey. The stark, largely barren continents and relatively simple weather patterns of the Tonian period stand in dramatic contrast to our richly complex modern planet with its diverse ecosystems and intricate climatology. This comparison highlights how thoroughly life has transformed Earth over the subsequent billion years, reshaping not just the visible surface, but the fundamental systems that regulate our entire planetary environment.